Okay, so I'm now going to record a follow-up lecture to the one that I gave introducing the WKB approximation. And in that lecture, I took a different twist on WKB than the book provides because rather than just simply present it as a means to approximate exact Schrodinger theory, I want to give you some impression of what it means to sort of question a paradigm and to try to imagine alternatives, because you're not just given quantum mechanics as a sort of a written on tables of stone, but you can have an imagination that says maybe there's something that's more complete or more satisfactory as a description of the microscopic world than what I've been given in this quantum mechanics. So just try to imagine alternatives, and imagining alternatives might convince you, on the one hand, of how difficult it is to improve on the established theory, but on the other hand, how important it is that we not just stick with what we're given, but we imagine alternatives. So let's take this tack again of WKB and try to reconceive of quantum mechanics in a new way by saying, instead of being given a wave equation, and we think of the operators in that wave equation as the fundamental objects of the theory, and that the solutions are just byproducts of what happens when you glue those operators together into an equation. That's the Schrodinger approach. Let's imagine that instead, what's fundamental about the theory is the particle trajectory. That follows from classical equations of motion. And when we go to describe them in terms of waves, we have to assemble a mathematical wave description that has certain features that were laid out for us by de Broglie. First is that they have to be described by an envelope, and I've drawn the envelope here by a dashed curve, and that dashed curve basically gives me a PDF. If I square the amplitude of the wave inside it, it gives me a probability density function of finding the particle at any given point in space. And I've taken the centroid of that and marked it as x. So classically, my position x of the particle now gets smeared out over some volume of uncertainty. But within that volume, there's more to be said about the particle than just that it's somewhere in there. It also possesses an oscillating phase, and that phase is the marker that marks onto the particle's description its momentum. And the momentum, of course, is related to the wavelength. Here I've drawn a crest-to-crest wavelength representation, lambda. If I take h over lambda, that gives me the momentum of the particle, and that's how momentum gets imprinted on this little wavelet. And of course, we all know that this picture isn't static. If you're sitting in a lab frame, then in the particle in that frame has a non-zero p, then it will also be moving along at a velocity non-relativistically given by p over m, and I represent that by v here. So what kind of a detailed mathematical form would this wave take? And that's what WKB provides us. Basically, it says we're going to write it. We're going to separate the two pieces, the spatial coordinate information. We're going to localize inside this amplitude function a of x. That's going to be slowly varying on some scale, and the fast varying part is going to be moved into the phase factor phi of x, where all the momentum information lies. So we have position information here in this real function, and normally one thinks of phi as a real function with an I extracted from it. And in that case, this is just a norm of 1. And of course, we can have either the positive or the negative square root of -1. This partition of the wave function into a real amplitude and phase is the essence of the WKB quantum mechanics that I'm outlining. And we know that to get the right classical mechanics, we need to have P related to the potential energy in any region in space and the total energy carried by the particle to implement energy conservation. This is the ordinary classical mechanics. What I'm not trying to show you here is some kind of an operator relation here. P of x is simply a classical function that tells me classically what the momentum of the particle is when it sits at x, given that the potential V depends on x in this way, and E is the total energy. And of course, what I've tried to outline here is that we can imprint on the wave an oscillating phase whose wavelength gives us h over p, provided that we make this phase phi have a derivative that is p divided by h. And so I'm just reviewing what we went over in class on Wednesday. Okay, so where does uncertainty in this quantum mechanics come in? It only comes in from the fact that this function a, or a squared, its modulus squared, has a width. And so that is a fundamental injection of uncertainty into WKB quantum mechanics. P, on the other hand, is not an operator. There's no commutation relations with x in this theory. And so P, just a function of x, is an ordinary function and has no uncertainty in it. Of course, you would, if you were to ask the more general question, not just what is P when the particle's at x, but what is P for the particle now, then you'd have to smear out x, which would by consequence smear out P, in as much as the P of x is a varying function. So what is this phi of x? Well, we've written that its first derivative is P. If I take the antiderivative of both sides, then you can see that I integrate P up to the upper limit of x, and this gives me the function phi of x. And I haven't specified the lower bound. It turns out that just adds a constant phase to the wave function that's global, and so it has no physical consequence that I've illustrated here. So let's apply this to an example. Let's take the free particle. Here is the simple case where P is just the square root of 2me, and I've set V to 0. Now my phi is obtained by integrating, and it's simple enough to set x equals 0 for the lower bound, in which case now my phase factor is just a constant times x. In a more familiar form, that constant can be called k, in which case taking both signs of the square root of -1, I'm allowed to have a general WKB wave function for this potential with a right-going wave, e to the ikx, and a left-going wave, e to the minus ikx, and each one of them carrying along with it its associated wave packet, a of x and b of x. Now there's no information so far about what those shapes should be, but presumably one shapes those to carry the position information that is required by the boundary conditions. And it turns out, you might remember that in as much as A and B are slowly varying, this is an exact solution of the Schrodinger equation. So WKB quantum mechanics agrees completely with Schrodinger in this case. Now, I haven't said what the meaning of A is, and so let's add a little bit of information about that. If the particle is accelerating, that is, not like this case with V equals 0, but if there is a force on the particle, then we'd expect its velocity to be changing. The faster it moves, the less time it spends in any spot in space, and so it would make sense that this slowly varying amplitude function, when I square it, should be a number that's proportional to 1 over the velocity, so that when it sits still, it spends a lot of time there, and the probability goes way up, and when it's moving quickly for a given distance, it spends much less time in that region in space. Make that quantitative, we're looking here at time per unit length, that's dt dx, which is 1 over dx dt, or velocity. When I take the square root of that to make it a, not a squared, then I get a factor 1 over the square root of v. Now in the case that I've chosen above here, this a and this b are written for a constant v, and therefore these would just be constants. But in the more general case that we'll see here in a minute, we're going to be needing to put in a variable amplitude, and it'll have the form c over the square root of v, or since p is the number we calculate here, let's just move the square root of m into the c and write it as c over the square root of p. Now this completes our prescription for writing down the de Broglie wave packet in this WKB quantum mechanics. Coefficient for the amplitude 1 over the square root of p, and then two arbitrary constant coefficients whose size is determined by the initial conditions that go along with this wave. A right-going wave, e to the I phi, and a left-going wave. And just remember, this phi is not just some unknown function. It, in fact, is nothing more than the integral of a perfectly well-defined function, p of x, which one may have to work hard to evaluate, but in principle, there's nothing complicated about p. It's just this, and so therefore it's integral. If v is continuous and smooth, then so is p. So let's apply it to the next least simple case, moving on from constant potential, the simple harmonic oscillator, in which case we'll just describe v by a parabola and adopt the common convention. V equals 1/2 m omega squared x squared. And we'll take the origin of the coordinate system to be the center of that potential. Here I am computing p of x. So I'm going to factor out a common factor, 2me. What that leaves me is a coefficient which is 1, after I factored that out, minus, now this coefficient here is this piece, 1/2 m omega squared, divided by e. Let me, since it has units of 1 over length, obviously, let me just write it as alpha squared. And just remember that this is 1 over length squared, so that this becomes length squared. And this is dimensionless, to which one can add a number 1. Now let's write down the explicit value for alpha here. And I've already mentioned it. Just interesting to notice that it has a physical meaning. If we look at this plot over here, here is the potential I just indicated. At some arbitrary, yet to be determined point, we identify the energy, total energy of the system here. That intercepts the potential at 2 points called the classical turning points. If this were a classical oscillator, it would oscillate up to here, at which point the potential energy would reach a maximum, and then it would reverse, go back, and swing to the other side. And this is the standard pendulum type motion of a simple harmonic oscillator. And let's call this classical turning point the point x0. If you just set this argument to 0, you find that it's simply related to the coefficient alpha through 1 over x0. Pressing on, what was the point? It was to calculate this phi integral. So let's take the p we just computed, factorized just as we did, pull out the constant coefficients. What do we have to do? We have to integrate the square root of 1 minus x squared. Let's rescale x squared and turn it into a dimensionless number u. And now this is a standard integral. The integral of the square root of 1 minus u squared, you might think by trig substitution, can be found easily, and that's exactly how to do it. Turns out that it has this inverse trig function and then a trivial term that comes from the boundary terms. And here are my limits. Notice that I've now committed what I want to have for the lower bound. I just decide for my lower bound to choose the classical turning point. And this is going to be something we do all the time in WKB. The most convenient reference point will always in WKB be a classical turning point. So we're going to set now, we're going to commit on what phi we want. We're going to set that value there to x0. When we convert to u, it becomes alpha x0. And alpha x0, since the reciprocals, is just 1. Let's substitute in now and take the difference to do the definite integral. And at the upper point, we have a variable function, and at the lower point, the constant. The inverse sine of 1, which is pi over 2. And now notice that with this phi now computed, we can just simply write down what the solutions of the simple harmonic oscillator will be in the WKB approximation, nothing more than 1 over the square root of b e to the plus and minus I phi of x. Now, because of symmetry, we even know how to glue these together to make the even and odd states, which have to be the eigenstates of H, the even ones and the odd ones corresponding to the combinations with the plus sign here in the exponent, plus the same one with a minus sign, that's even parity, or minus, that's odd parity. Notice that this wave function doesn't remind us at all of a Gaussian times the Hermite polynomial, which are the familiar forms that we've already gotten used to for working with a Schrodinger equation. So we see now that this is really a distinct quantum mechanics. WKB is not simply repeating everything Schrodinger gave to us over again. There are not equivalent theories. And we have a slightly more complicated exponent here. It doesn't look like a Gaussian. And notice that there's no Hermite polynomial sitting next to it. So now one might guess, perhaps this quantum mechanics might be more correct, or there might be a region of application which causes this to be better than Schrodinger at some point. To address that, we have to ask, where do they disagree? And this is, I just touched on in class on Wednesday. I repeat it again here. Look near the classical turning point. So what is P? Well, P reaches a maximum here. It reaches 0 at the two endpoints. But now what happens to this solution that I've written down here when P is 0? Well, the answer is, because this has unit amplitude, it's never 0. Therefore, we have a limit as we approach that classical turning point from the classically allowed side, that we have something of order 1 over something of order 0. And this is divergent. So this is our problem. Classical turning points result in divergent wave function solutions in the WKB quantum mechanics. And here's what I'm illustrating. Let's contrast that with the known solutions that behave just fine at the classical turning point for Schrodinger. This is, I've tried to sketch here the n equals 4 solution, where what I call the n equals 0 is the ground state, n equals 1 the first odd parity, n equals 2 the second excited state, and then 3 the second odd parity. And this is then now, this one here actually has 4 nodes in it, and it's called n equals 4. You can see it's an even parity state, as you expect. It has all the right behavior. It oscillates, okay? And this is due to the Hermite polynomial that's built into the n equals 4 solution. And you can see outside the classical turning point, the behavior becomes more and more similar to what one expects for a tunneling wave function, exponentially damped and going to 0 smoothly. Notice nothing is going wild here at the point where the wave function passes through x naught. On the other hand, here's WKB, kind of satisfying to see that the number of bumps and wiggles looks similar. So there is a resemblance to the true solution, well, to the Schrodinger solution. Let's not commit ourselves on either side. But notice what happens as it reaches the classical turning point. The WKB solution goes absolutely wild. So maybe now we can say, since they disagree wildly and one of them seems pathological, the other one seems perfectly well behaved, maybe WKB isn't really a replacement quantum mechanics, maybe it's just an approximation, and it's an approximation one can treat seriously, provided you stay away from these problem areas. And that's going to be the approach we're going to take. These singularities are not physical, they're an artifact of the choices that were made in adopting this quantum mechanics. They turn out to be not physical. They don't appear in nature. We don't see anything in quantum mechanics that suggests something special is happening at the classical turning point. And so now let's look and see if there is any suggestion by comparing in detail this solution to the true solutions to Schrodinger's equation, and see if there's a suggestion that perhaps there should be a approximation that looks like WKB to this simple harmonic oscillator Schrodinger problem. Here's my full Schrodinger problem, where instead of writing psi, I now substituted in a either plus or minus I phi, and taking the first derivative, taking the second derivative. I believe I went through this in class on Wednesday briefly, but here we go through it again. This is just that same, this is Schrodinger time independent, written in the factorized form, and so the spatial derivative applies both to the a and to the phi, and you can see second and first order derivatives because of the chain rule. If I take the imaginary part of both sides, since there's no imaginary here, once I get rid of the phase, then it has to be 0. On this side, I get to pick up two pieces. Turns out these two pieces, when considered together, are a total derivative. And what that tells us is that the thing inside the braces has to be constant. If I set that to a constant and call it c, that tells me that the amplitude a is equal to c over the first derivative of phi. We call that first derivative p, as we will see, and this is nothing more than telling us that Schrodinger insists that if we factorize the wave function into a e to the I phi, then a should be equal to a constant divided by phi prime. Interesting. Okay. So far no approximation. Our WKB is looking very much like Schrodinger, but it comes now to the real part, and now there is no I on either side. I've dropped out the factor e to the I phi so that I can compare the coefficients, and you can see here that I'm going to get WKB, but only by dropping an extra term. So if I set this A double prime to 0, then I find that there are two roots, phi prime equals P over H bar, and phi prime equals minus P over H bar. And these are these two solutions here. So if I integrate this with respect to x once, then you get the form that I suggested earlier based upon a more heuristic approach to de Broglie waves. And we can see that Schrodinger also gives such a picture for phi, provided that I'm willing to drop the double derivative of a. And ignoring a double prime in solving the Schrodinger equation for the a e to the I phi form does turn out to be a good approximation in certain places. It just breaks down near the classical turning points. Okay? So this is sort of a fundamental now understanding of what we've done. We haven't replaced Schrodinger equation. We haven't found another way to solve the Schrodinger equation, but we found a way to approximate it. And we can expect that anywhere we're inside the classical allowed region and away and keep a respectable distance from the classical turning points, that this should mimic the solution from WKB should mimic the solution from a full first principles Schrodinger uh, uh, differential equation solution. Now it turns out that Schrodinger gives a wave function solution not only in the classical allowed region, but in the classically forbidden region. So we might ask ourselves, well, what are we going to do for understanding the wave function behavior of WKB is our tool. And it does turn out that once you go out into the deep into the classically forbidden region, away from the classical turning point, WKB again recovers sensible behavior. That is the 1 over square root of P. Now P has become a complex number, but the square root of a complex number is perfectly reasonable. And if you work it out, it turns out that a second solution is found using the WKB prescription, it also looks like 1 over the square root of p, but now p is the modulus of an imaginary square root. And likewise, up in the exponent, this is a phi, but now the phi doesn't have an I beside it because it has to be an exponentially damping or exponentially rising wave function. As we know, has to be the case when you're in the tunneling regime. And what is this phi? It's nothing more than, factoring out an imaginary part, the original phi that we had. It's the integral of p times 1 over h bar, except that p inside the square root has reversed its sign because now you're in the classically forbidden region. So notice that instead of writing 1 minus alpha squared x squared, we write alpha squared x squared minus 1 to make sure that the square root here is still a well-behaved real function. I've pulled out the I. Okay, this leaves only one question. We've got WKB working in the classically allowed region. We've got it working in the deeply classically forbidden region, but in the crossover between the two, we have this blowing up problem. What do we do at the crossing points, at the turning points? And this is the subject of the next lecture. So I'll be continuing on with this in the next lecture and pausing now.